Hi guys, today I'm going to talk to you about electron configuration. So you will need a highlighter, a pen or pencil. You also need your periodic table that you normally use. And from your notes, don't forget to print out a blank periodic table today. And don't forget to grab a notebook, sheet of paper, so that you can practice electron configurations on it. So let's get started by defining what electron configuration is. Electron configuration tells you the distribution or location of electrons in an atom or an ion. There are rules for filling electrons in an atom. The most general rules are that electrons fill an atom from the lowest energy orbital to the highest energy orbital. And this should make some sense to you because when we talked about atomic spectrum, notice that we talked about the lowest energy orbital being closest to the nucleus and the highest energy level orbitals were furthest away from the nucleus. In an atom, no two electrons can have the same 4 quantum number. That's the same as saying that no two electrons can have the same address. Okay, so that's what I'm talking about when I say quantum numbers. I'm actually saying address. There are some specific rules that electron configuration follows. The first rule or principle is the Aufbau principle. And Aufbau is a German term and it literally means starting at the lowest level. So electrons fill the lowest energy orbital first, and then they fill higher energy levels. Keep in mind, you guys, that the electrons have a negative charge, and the nucleus has a positive charge due to the protons. The electrons are naturally attracted to the nucleus, and it takes less energy for them to be closer to the nucleus than to be far away from the nucleus. The next principle that I want to talk to you about is called the Pauli exclusion principle. And the Pauli exclusion principle simply says a single orbital may hold no more than 2 electrons, which have opposite spins. Now this makes a lot of sense because you have electrons that have a negative charge. So these electrons that are close to one another in the atom will actually start repelling each other. What happens is that if these electrons happen to switch their spins, where one is spinning up and the other one is spinning down, then these electrons, they're still repelling one another, but the repulsion is not as much now because of the opposite spin. So I call this the shoe box theory. Okay, and I want you to draw a shoebox. I'm going to draw my feet here since I'm for my artistic abilities. Okay, well, that's good enough. But so notice that in a shoebox you have one shoe that's fitting that's facing one direction, and if you want to fit the other pair of the shoe, then you have to put it in the opposite direction so that both of those shoes can fit in there. So that's my shoebox theory explaining the Pauli exclusion principle. The next theory or rule that I want to talk to you about is actually called Hund's rule. So Hund's rule says when several orbitals have the same energy, one electron enters each orbital until all contain one electron with the parallel spin. Okay? So I call this the passing out candy rule. So what this means is that let's say you have 3 people and you have 4 pieces of candy. What you're going to do is that you're going to take the candy and pass it to all 3 people. And then if there's any extra left over, then you're going to go back and pass the remaining candy to those people. And so that way, every single person gets some candy. Okay, so that is Hund's rule. Electrons do the exact same thing. They will enter an orbital, and each electron will take an orbital until all the orbitals are filled up, and then electrons will go back in there and stack up with one another. And let's say right here, when a group of orbitals have the same energy, they are called degenerative. Okay? Okay, so the last rule or principle that I want to talk to you about is Heisenberg's uncertainty principle. Okay, and it says here that it is impossible to know the exact position and velocity of an electron. Okay, and what that means is that an atom is very fluid. So things are always moving inside an atom. Electrons are moving around. Even inside the nucleus, you have the protons and the neutrons that are moving around. And so you can't really know the exact position of that electron because it's always moving around. If you do want to know the exact position of that electron, then you've got to stop it in order to know its position. But if you stop it, then realize that you are messing up the velocity of that electron. Okay? So if we know the position, then we mess up the velocity. But if we want to see that electron in action moving around, then you can't know the exact position because it is constantly moving around. So that's Heisenberg's uncertainty principle. Okay, so grab your blank periodic table and let's talk about electron configuration. I'm going to use the Bohr model to talk about the location of these electrons. I do realize that we normally use the quantum mechanical model to talk about the distribution of the electrons in an atom. But keep in mind that the quantum mechanical model is a probability of where these electrons are located, and it's a lot easier to discuss the location of the electrons using the Bohr model because it's more concrete. Okay, so you have your periodic table right here. Okay, normally when we talk about the location of these electrons, we talk about how these electrons are, here's the nucleus, and how these electrons circle the nucleus in something called energy levels. Okay, so you can have electrons in any one of these energy levels, and they're just circling or they're around the nucleus. Okay, well, the periodic table is actually set up according to this, and let's just say that this is energy level number 1, 2, 3. Clearly, I can have more energy levels. And your periodic table is actually set up according to this model. So if we're looking at our blank periodic table, keep in mind that when we talk about the nucleus is actually right here. Okay, it's right here on top. And then you have energy levels that are circling the nucleus. So you have energy levels that are going all around the nucleus. Okay, so you only see this from one direction. We can just say that you see this from just this direction and not the entire circle. Okay, so if we're looking at this periodic table, your energy levels are actually the periods on your periodic table. So you have energy level 1, energy level 2, 3, 4, 5, 6, 7. So in actuality, there are really 7 energy levels. So go ahead and write here next to this, and let's see if I can move it. Next to this, write energy level. Okay, so before I go any further on with electron configuration, I just want to remind you that, remember, electron configuration tells you the location of these electrons. So typically, when we talk about location, we talk about address of some place. When we write the address of something, we usually have a number, the street name, and then we have the zip number, right? Okay, so that's our typical notation to write an address. Well, when we write electron configuration, there is also a notation that we follow. The notation is usually a number, just like you have, and then you have a letter that tells you the street name, and then of course there is a number here that it acts like a zip number. So this right here, the first number, is actually the energy level. Okay, the S is actually your address, but it can also be known as your orbital. And there are 4 different types of street names or orbitals, and it's called the S, P, D, and F. Okay, and then this number here tells you the number of electrons that are present. Okay, so this is a typical electron configuration that we have, the notation that we use to write our electron configuration. So like I said, we have a total of 7 energy levels, and these are the periods on your periodic table. Okay, now as far as I'm talking about the street name or the address, we have SPDF. So on your periodic table, you have the S orbital, and you have the P orbital, you have the D orbital, and then you have the F orbital. Okay, before we go any further, I want to talk about the periodic table and how this periodic table, how you have different types of periodic table. Now, this is the element helium that you have. And on most periodic tables, you see helium right above, right where the noble gases are. And that's because helium is a noble gas. It is very stable, and it follows the same properties as the other noble gases that are in the same group or family. That's why helium is usually placed there. But some periodic tables actually move helium from there, and they put helium right here. So you can do the same thing and go ahead and write helium right here. Well, the reason why we want to write helium here is because of electron configuration. Now, helium, although it's a noble gas, its orbital that it has is simply the s orbital. And that's why you usually see a blank, because this blank area is for helium. Okay, so when we talk about the p orbital, we're talking about the p orbital starting from here to from the boron group all the way to neon and the other noble gases down. Okay, we're not talking about helium in the p orbital. The transition elements, you guys, are the d orbital, and then of course the inner transition elements are your f orbital. Before we start marking up the f orbital, I want to tell you that there is an extra column that is in the f orbital, and that's this column right here at the very beginning. This column actually belongs to the 2 elements. The first tile belongs to lanthanum, and the second tile belongs to actinium. Both of these elements are placed in the periodic table most of the time down here, just like the helium is usually placed in your periodic table with the noble gases. The reason why these 2 elements are placed with the f orbital or with the inner transition elements or inner transition metals is because both of these elements have the same properties or have similar chemical properties as the other inner transition metals. And so they're placed down there. But in reality, just like helium, when we talk about electron configuration, belongs up here, both of these elements actually belong right here. So when we talk about electron configuration, these elements are over here, and your true f orbital actually begins after those two tiles all the way down. Okay, so now that you know that, let's start talking about the parts of the orbital. Okay, so let's start talking about the number of electrons that are in each orbital now. So in your s orbital, you have s1 and s2. And this 2 happens to be the maximum number of electrons that are in the s orbital. You have your p orbital. You have p1, p2, p3, p4, p5, and then p6. This 6 right here happens to be the maximum number of electrons in the p orbital. The d orbital is d1, d2, d3, d4, d5, d6, d7, d8, d9, and d10. And this 10 happens to be the maximum number of electrons that can enter the d orbital. And then your f orbital is f1, f2, f3, f4, f5, f6, f7, f8, f9, f10, f11, f12, f13, and f14. And what do you think that last number is? That last number is the maximum number of electrons that you can have in the f orbital. I just want to clarify that the maximum numbers that you have in the s, p, d, and f is the maximum number, this number that we circled. You can certainly have you can have less than that number of electrons in that orbital. So if we go back to the s orbital and let's start writing the electron configuration. Keep in mind that the notation for the electron configuration is you write the energy level, the orbital, depending on whether it's s, p, d, f, and the number of electrons that are there. And what's interesting is that each tile on here, or each element on here, has a certain electron configuration that it ends in. So the first tile right here, since this is the energy level number 1, we are going, and I'll use a different pen, we're going to write 1 for that first energy level. And since it is in the s orbital right here, we're going to write s. And s1, we're going to write a 1 right here. Now, keep in mind that when we wrote s1, that is to say that every single element that is in this group right here has the same ending, it ends in the same orbital number. So this group right here ends in s1 orbital. This group right here will end in s2. Any elements that are in the boron group, carbon group, nitrogen group, the chalcogens, or the halogens, or even the noble gases will end in their respective orbital number. So let's say that the carbon group, which is group 14, will end, every single element that's in the carbon group will have the ending of P2. So for helium, it is energy level number 1 right here, the s orbital. In this case, it's s2, the maximum number of electrons. Okay, and then we have here, and then we notice we don't have anything else in energy level number 1. So now we're going to go on to energy level number 2 and write a 2s1, and this is going to be energy level number 2 again, but now it's an s 2. Okay, now if you go straight across, now we have the first p orbital that is starting. So again, we're going to write 2 because it is an energy level number 2, but now it is P1. Energy level number 2 again, P2. Energy level number 2 again, P3. Energy level number 2, P4. Energy level number 2, P5. And energy level number 2, P6. And now we're done. So we're going to go to the third period, or the third energy level. So we're going to write a 3 here. And this is 3s1. So we're going to write 3s1. Because we're in the third energy level, we're going to write a 3 again. And because we're in the s2 orbital, we're going to write here s2. The d orbital doesn't start yet, but we definitely have the p orbital. So energy level P1, 3p2, 3p3, 3p4, 3p5, and 3p6. Now we're going to go on to the fourth energy level, and we're going to start with 4s1 and 4s2. Now we're going to start the d orbital, and d orbital is a little different. Notice that for orbitals s and p, you really didn't have that many electrons, but d orbital, we're getting a total of 10 electrons. Well, these 10 electrons all have a negative energy, and so these electrons will now start repelling one another. So truly, because there are that many electrons and they're repelling one another, the d orbital tends to have a higher energy than the 4s orbital. For that reason, but yet when we talk about the energy level, these three, the 3d energy level is actually in the third energy level. So instead, we usually say that it is the energy level for D is usually the energy level that D is on minus 1. Okay, so in this case, when we start writing the d orbital, it's the energy level 4 minus 1. So this would make it the 3d1. Okay, 3d2, 3d4, 3d, oops, let me fix that. Okay, I fixed it. Moving on, 3d5, 3d6, 3d7, 3d8, 3d9, and 3d10. And keep in mind, you guys, this is only true for the d orbital, that they seem to have their energy is a little bit higher. But when we get back to the p orbital, it's at the same energy level. So now we would say that we're back to the fourth energy level, P1. So 4P2, 4P3, 4P4, 4P5, and 4P6. Okay, so that is true for all the d orbitals. So if we have here, this d orbital starts on the fifth energy level, minus 1 would give us 4d1. Moving on to the next energy level for d, lanthanum, would be 6 minus 1, and this would be 5d1. For actinium, you're in the energy level 7, so 7 minus 1 would give us 6d1. Okay, so now let's talk about the f orbital. But before we do, go ahead and get a highlighter and highlight this line that is coming after the lanthanum and actinium elements in the f orbital. So highlight this line, And also highlight the line that comes after lanthanum and actinium in the d orbital. And what that line actually is saying is, in reality, the f orbital is not down here, but rather it actually belongs over here. So take a pen and draw yourself an arrow that's saying that this f orbital actually comes right after lanthanum in energy level number 6 and actinium in energy level number 7. So what this is actually saying is that the f orbital actually squeezes it right here where this yellow line is. So if we were to draw the real periodic table, the real periodic table would look a little different than what you guys see. You would have the s orbital, you have the f orbital, the d orbital, and then you have your p orbital right there. So the f orbital actually belongs between the s orbital and the d orbital. But we don't have our periodic table that looks like this. Instead, usually you see your periodic table looking a lot like this, where the s orbital, the d orbital, p orbital, and then the f orbital is down there. The reason why we draw our periodic table most of the time like this is because this periodic table saves us space. This is too big to actually fit on a single sheet of paper. So in order to save space, we don't draw a periodic table like this. Rather, we draw a periodic table like this. But if we're really talking about electron configuration and how to write electron configuration properly, you need to understand that the f orbital actually squeezes in between the s and the d orbital right here, and these two columns would actually, or the f orbital, these two columns of the f orbital would squeeze in right here after the lanthanum and the actinium in energy level number 6 and energy level number 7. Okay, so if we were talking about this, we would say that the f orbital has a total of 14 electrons. And just like the d orbital, these 14 electrons are repelling one another. Because these electrons are repelling one another, it takes a lot of energy. And so these electrons actually move down in the periodic table, and they take up a lot more energy for these electrons to be in these energy levels. So in reality, just like it's d minus 1, the f orbital is actually f minus 2. So this the lanthanum orbital or element. So you would have the element cerium and thorium that would actually, and all their other elements that follow them, would actually squeeze in here. So cerium would actually be in energy level number 6, but it is 6 minus 2, so that would be 4f1. Okay, and then it follows, if this would be 4f2, 4f3, 4f4, 4f5, 4f6, 4f7, 4f8, 4f9, 4f10, 4f11, 4f12, 4f13, and 4f14. Okay, and you would do the same thing with thorium. Thorium would be after actinium. It would go right here. And so thorium is in energy level number 7. So it'd be 7 minus 2, which would now give you 5F1. Okay? And it would go all the way down to 5F14. Okay? Okay, so now that I've explained to you about the electron configuration on the periodic table, grab a sheet of paper and let's practice some periodic table, writing some electron configurations for some of the elements in your periodic table. Okay, so let's start with the first element being hydrogen. Okay, so if you're looking at your periodic table, this is what you need to be looking at. Right now, you guys, we're going to talk about neutral atoms. So in a neutral atom, hydrogen usually has one proton in it. Well, if it's a neutral atom, it's also going to have one electron in it. So here's the one proton. So if we're going to write the electron configuration for it, hydrogen is right here on your periodic table. And so the electron configuration is that it is 1, it's 1s1. So that's it for hydrogen. For helium, there are the atomic number is 2, so it has 2 protons and then 2 electrons because it is a neutral atom. So we want to write the location of both of these electrons. So helium is in energy level number 1, and it is in S2. Okay, S2. So when I draw the Bohr model for this, for hydrogen, the Bohr model would look something like this. You've got your nucleus right there, and then you've got your energy levels that are going around it. There's 7. I'm not going to draw all 7 of them. But then you have the first electron from hydrogen that is right here. And then if we're talking about helium, helium has 2 electrons in it. Well, the first electron's right here, and then the second electron is right here. You don't need to write 1s1 in helium, because when you write 1s2, this 2 is actually including the electron from all the other s orbitals. In this case, it's the other electron from the s orbital. So this is from s1, this is from s2. So this writing 1s2 actually includes writing 1s1. Okay? Okay, so let's continue on with our electron configurations. Let's write the electron configuration for lithium. Lithium is right here on our periodic table, so go ahead and write lithium right here. And if you're looking at your periodic table, it has 3 protons in it. So if we're talking about a neutral atom, it has 3 electrons in it. So lithium has a total of 3 electrons in it. The electrons, we're going to start off with the very first energy level that's closest to the nucleus. So we're talking about energy level number 1. And this energy level number 1 has 2 electrons in it. Notice that this energy level does not have a p group. So we go on to the second energy level, which is where helium is. Helium is located in 2s1 orbital. So we're going to write 2s1 for lithium. So if we actually draw the Bohr model for lithium, it's got 2 energy levels, so it's got 2 circles in it. And the electrons from 1s2 will be located right here. From 2s2, with that 1 electron would be located right there. So lithium has 3 electrons. You can add these exponents up, and it should give you the total number of electrons. In this case, it's 3. In our Bohr model, we could also add up the dots here. 1, 2, 3. And that should give us the total number of electrons there also, which is 3. Let's do beryllium. Beryllium is 4. It's located right next to lithium on our periodic table, so go ahead and write Be. Let's write the electron configurations. We're going to start off closest to the nucleus, which is 1s2. Doesn't have a p group. We're going to go to the second energy level, and we're going to write 2s2. Okay, 2s2. And we could draw our Bohr model or continue with this, and so we would draw our second electron right there for 2s2. Okay, let's go on with boron. Boron has a total of 5 electrons, so boron's right here. And start off with the one that's closest to the nucleus, the energy level, and so that would be 1s2. Then we'd start off with the second energy level, be 2s2 for that orbital. But boron's in the p orbital right here. But it's in the same energy level, so it's in 2p1. So it's in 2p1. If we're drawing the Bohr model for this, it's got 2 energy levels, 1, 2, and we're drawing our electrons. There are 2 electrons in the first energy level. There are 2 electrons in the 2s energy level, but the second energy level, or energy level number 2, has 1 electron in the p orbital. So I'm just going to draw that right there. Okay. Let's do another one. Let's practice phosphorus. Okay, so phosphorus, the number of protons in a neutral atom is 15, so it's got 15 electrons. We're going to start off with the first energy level. That's 1s2. Doesn't have a p orbital. Start off on the second energy level, so we're going to go to 2s2, and then we're going to go to 2p all the way to 2p6. Okay, we're going to go to the third energy level, so the 3s2, and then in the third energy level we're going to go to 2p3, because that's where the element phosphorus is. It's got 3 electrons in the third energy level p orbital. Okay, so it's going to be 3p3. So we can't stop in the middle of these orbitals, anywhere in the middle. We just need to keep the energy level and the orbital. We need to focus on how to write, keep in mind the energy level and the orbital. Okay, so if I'm drawing the Bohr model, I've got 3 energy levels, so I'm going to draw 3 circles. And you don't need to draw the Bohr model each time. I'm just drawing it so that you can actually see it, the electrons. Notice how our electron configuration notation is increasing as the number of protons or electrons is increasing, and you can also see that in our Bohr model. So the first energy level has 1s2, has 2 electrons in it. 2s2 also has 2 electrons, but then you have 2p6, so we need to include those 6 electrons in the second energy level. Then you have 3s2, so in the third energy level you have 2, but you also have the p group that's there, but this is now 3p3, so we're going to draw our 3 electrons. And I like to separate them from each side to make them equal, because just so that you can see it. So if I count up the number of electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, that is the same number of our protons, which is equal to electrons, 15 electrons. And if we add up the exponents, that should also equal 15 electrons for us. Okay, so let's do the next one, which is, let's do calcium. Calcium is 20. Calcium is right here in the 4th energy level. So we're going to start off with 1s2. And if you know how to do this now and you're getting an idea, just look up when you are done, okay? Okay, so look up, and it's 1s2, 2s2, okay? And right here, 2s2, 3s2. So we've got 1s2, we've got 2s2, we've got 2p6, we've got 3s2, we've got 3p6, and then calcium's right here, so we've got 4s2 right here, okay? And I could draw the Bohr model for that. Okay, so now let's do another element, scandium. Scandium, which is 21. And scandium, notice, is right here in the d orbital. So it is right here. So go ahead and write the electron configuration yourself up to 4s2. Don't go any further on. I need to tell you. Make sure you are doing everything else right. Okay, look up, you guys. So I have my electron configuration written all the way to 4s2, which is calcium. But scandium is right here, the next one element over. Notice for scandium, it's in 3d1. So we are going to actually write 3d1. Okay, so we're going to write 3d1. Let's pick another element. Now let's write the element right here. Let's write the element bromine, Br. Okay, that's in the 4th energy level. So bromine has a total of 35 protons. In a neutral atom, it would have a total of 35 electrons. So we start with 2s2, 1s2, 2s2, 2p6. Oh, hold on. Let me write on this sheet of paper for you guys. Okay. So it is bromine has 35, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and I now have the d orbitals, but the bromine is right here in the p orbital of the 4th energy level. So I'm going to continue on. I'm going to write 3d10 to include all the elements of the d orbital. So I'm going to write 3d10, and then I'm going to continue with the 4p. So it's going to be 4p5 that I'm going to write. Okay. And I'm going to stop the video and draw the Bohr model for you real quick. Okay, you guys. So now I have drawn the Bohr model for it, and I'm going to zoom in for you to see. But if you look at this, you can count 35 electrons. And if you count this in total, there's a total of 35 electrons. Notice that in the S1 orbital, I only have 2. In the 2 in the 2 energy level, I have a total of 8 electrons. But when I get into the the 3rd energy level, now I have a total of 18 electrons. Okay, and that's because of the 3D. So in the 3rd energy level, you see 10 extra electrons that have been added. And then when we get to the 4th energy level, I have a total of 7 electrons, and you can see that 1, 2, 3, 4, 5, 6, 7. And those are my valence electrons, or electrons in the outer shell. Okay? Okay, so let's do something a little bit more complicated. How about if we do tungsten 74? And on your periodic table, tungsten 74 is located right here. It's in the 6th energy level. Of course, it's 6 minus 1, which is 5. It's in the d orbital, so 5d. and it is 5d4. So that's where we're going to stop for tungsten. Go ahead and write the electron configuration for tungsten, and then look up once you are done. Okay, so don't forget, you guys, your d orbitals come in for other energy levels also. So I'm going to include that. Okay, so look up, and you should have gotten all the way to 5d4. So in the previous example for bromine, we stopped at 4p5, but this is actually 4p6, and then you go to 5s2, okay, 5s2, and then we go to 4d10, and we write all the way to 4d10. And then we go back and we write 5p6. That's what I have here. And then the next energy level is 6s2, which is what I have written here. And tungsten is right here, but it's actually 6 minus 1, which is 5d4. And that's where I end up. And 5d4 for tungsten. Okay? Let's do something a little bit more complicated than tungsten. Let's do uranium 92. So if you, on your periodic table, if you go to your periodic table, uranium's right here. It is in the same row as actinium, and it is in the third, it's the third electron in the f orbital. So you've got uranium. But something different happens with uranium. Uranium is in the f orbital. And notice we had to actually change how we wrote the periodic table for the f orbitals. So go ahead and write the electron configuration for uranium, but when you get to 7s2, stop, because something very special happens, and it only happens to elements that are in the f orbital. This rule doesn't apply to any other elements on the periodic table except for the elements that are in the f orbital. Whether it's in the 4f1 series all the way to 4f14, or in the 5f1 all the way to 5f14. So if any elements are here, they would follow this exception. Okay, so let's do one more. Rutherfordium, and that is RF, I think it's 104. Yeah. So Rutherfordium is right here on your periodic table. It's in period 7, and so let's write the electron configuration and look up when you're done. Keep in mind that the exception to the rule is here, and actually the exception of the rule would not be here in this one, because now we're talking about the d orbital. Okay, so okay, look up. So notice that I went from 7s2 for Rutherfordium to 5f14, where for uranium I went to 6d1 first, and then I went to 5f3. The reason why this is different is because uranium was in the f orbital. So this d energy level, 6d1, comes in, and then I go back to my f orbital, which squeezes in right after the 6d. but Rutherfordium comes after it's in the d orbital first of all, and then it comes after actinium. So I'm just going to include all of this d orbital, and then I'm going to have this 6d to come in for Rutherfordium. So 6d2 right here. So keep in mind that the exception to the rule only applies for elements that are in the f orbital. Okay, you guys, so this concludes my lecture on electron configuration, and I hope it really helps you. Thank you. And just to give you, make this smaller. Okay, this is my electron chart, periodic chart, the blank one that I wrote up for you guys. Okay, thank you.